think let's start now. Yeah. Okay. So, since this is a kind of mini course, I will try to start with the preliminaries and definitions. And in particular, the definition, the way that I will put, you don't find this way in the literature. And today I will just introduce what it is. And put some theorems and try to explain the structure of the course, and also fix the notations. So at the end of the day, we will start with the family of projective varieties, and most of the course we will not care about the degenerations, because still in the smooth families we will have some challenging problems. Maybe let's say the xt, t to the t, then this will be basically this one pi minus 1 over t, and everything for the moment our complex numbers, but at least for one conjecture in the middle of today's course, we will consider also our K subfield. And okay, so with the different notations I will use frequently, then n will be the dimension of the fibers. And then today I will just try to introduce the general theory, but actually the theory is much more useful when you go to examples. One main example which I will consider, the full family of hypersurfaces of degree d and dimension equal to n. And what I mean, if you have this homogeneous polynomial of degree d, let's say so alpha will be alpha 0. I'm writing all these because these notations will appear on an course. Alpha n plus 1. So this will be the notation for the monomials. X0 alpha 0, x n plus 1, alpha n plus 1. And that then this degree is d, so d is the sum alpha 0, alpha 1, alpha n plus 1, d. So the sum runs over these objects, and frequently I will use these FT notations also. So at the end of the day, xt is given by the projectivization of ft equals to 0 inside so this one. This given by 0. And at the end, what is this? This T is just the parameter space of all this T alpha. So T is, in this case, it will be just Cn minus some discriminant And T belonging to this one, this T alpha, this collection of all these T alphas. And this discriminant just controls the singular hypersurfaces. Okay. At the end I will give some suggestions regarding this example, but let's push forward. So something, sometimes I ask people in my students in algebraic geometry, and they don't know this very basic theorem, but at the end the Englishman's liberation theorem. It doesn't matter what it is, but at the end what this theorem will say, that these xt's and these all x, they are, from the C-infinity point of view, they are the same object. There is no difference between them. Of course, the analytic, algebraic structure is changing. And so they are isomorphic in the C-infinity category. And maybe if I want to say a more precise statement, if you have this T space, if you take T here, you take S here, and if you take pass, and remember that we are outside the singular locus. If you take a pass from here to here, through this pass you can, by Cattani-Deligne-Kaplan here, by Erishman theorem, you can find the C-infinity isomorphism. These isomorphisms in this are not unique, but if you pass to homology, then this pass will depend on the homotopy class of the outcome. What it means that at the end, if you just move this pass, there are this map is not at all canonical, but this will be this map will be the same. And this is the beginning of Cattani-Deligne-Kaplan theory, monodromy, and so on. I will be back in particular examples. Okay, but okay. So maybe another notation. M will be a fixed number between the top cohomology 2n, because n are the dimension of the variety and between 0. And yeah. Okay. So let's. I will fix a variety in my family. In the case of hypersurfaces, will be Fermat, but usually fixing the point will make the things easier. So what this means, and then when I choose delta 0 to h m x0, then but we can choose a homologic class, and by this argument, then one gets from here, one gets, let's say, delta, which will be delta the monodromy T. Another notation that I will fix here, T. T means small neighborhood of T. And this small name means the usual topology. I will also need a Zariski topology, but this means the usual topology, not the Zariski one. I will regard this T both as analytical, complex manifold, and the algebraic variety, and this switch between analytic, holomorphic context and algebraic would be important in the context of Loci. So when I fix a cycle, then I have this monodromy of this guy, And if this very picture is very old, these books of Cartesian theory, you can find it. So, for example, if you, this is your x0, then if you take delta 0, then of course you can go to the nearby fibers. Then you have this delta t. Again, another fixing of the notation. Okay. So what else we need? This let's say homology bundle. Let's say let's divide it by h and h. See what is this? Well, I will just do it the intuitional way. So, okay, maybe. So I have to look at this for pi. Okay, I will not use this pi here, so I will put here for pi. There are two different pi. So the fiber will just the cohomologies. And something and let's say this notation h n theorem x over t. At the end, it will be just let's say sheaf of holomorphic sections to this bundle of the homology bundle. So something that, well, when I'm using a cohomology, then it is in the infinity context, but you see that I'm using the word holomorphic, and later I will use also the algebraic. And this topic we will written back during the course, that this kind of object, let's say after protendic, and it's developed by Perry, and maybe the others also. So, this let's say cohomology bundle can be defined in the framework of, so your family, the whole family defined over a field. And for example, in the case of hypersurfaces, the family itself is defined over a rational number, let's say. And so this topic I will return because I will need to really represent differential form by algebraic. I know that many people in physics, canonical context, they just have algebraic differential forms. But the idea is that you can do in general, and really you don't need to see infinity forms to define this object. This was the beginning idea for people like Protendic-Deligne to produce more other cohomology theories. But so the point is that for today I will just I will allow myself to use the whole this guy as either holomorphic bundle or algebraic, and I will talk holomorphic section, algebraic section. But the precise meaning will appear will be defined during the course. And in particular, this will be let's say this will in the scatter over a field K. This will be locally free algebraic sheaf Okay. But so in order to define the Hodge loci, so let's call all what we mean by our periods. So for this one, omega. So usually omega will be an algebraic section. And when I'm talking about algebraic section, it will be in some Zariski neighborhood, a section of H on theorem xt. This will be basically differential forms. So basically we will have an omega t in t. Let's say in a Zariski neighborhood of 0. Let's just focus on 0. And then we will have this t. Despite the fact that I'm using for usual topology, at the end this is defined for t in the Zariski neighborhood. And then, okay, I'm almost finishing fixing the notation a little bit more. Then I will have this notion of so what will be the periods? Periods is just this will be this integration. So one important fact about this period, this will be they will be holomorphic functions. They will be holomorphic function in the neighborhood of 0 and t. And okay, so let me. So in the same time when the algebraic theorem homology was developing, so for instance, the fact that this is holomorphic, you must really you cannot take any infinity section. There are some special section called algebraic sections or holomorphic sections that at the period become holomorphic. And this is many examples of periods this appear in the Calabi-Yau context. But maybe let's me introduce the last, almost the last notation for definition of the Hodge locus is Hodge filtration. Let's fix the notation for Hodge filtration. The literature sometimes they will use different notation. So this will be. So again, okay. This. Before we do Hodge filtration, let's say the Hodge decomposition. So there is a natural decomposition. H, P, M, minus E, H, 0, M. So something which was clear at the end, that something like Hodge decomposition is purely analytic. You cannot define, let's say, starting from arbitrary field of characteristic 0 of a field, or let's say 0. Of course, you can also a little bit go to other characteristic, but let me just stay track is 0. So something like this, for instance, you define a harmonic form which belongs to the complex algebraic geometry, and really to bring to do something like this in the purely by algebraic methods means just using polynomial would be kind of impossible. But the something maybe observation due to again going back to Cattani-Deligne, that the Hodge filtration is much more natural to algebraic geometry. This means that if you make the sum from here, then this FP, and then let's call this one FP HM around XT. Then you can define this filtration in the framework algebraic geometry. again, these things I will be back because I will need to do computation, and then I have to really define what is algebraic theorem homology. But for the moment, just if you know, just skip the complex intuition. And at the end, we will have the subshift. This will be just locally free subshifts of this kind. And yeah, for okay.
Sorry, can you define a period? Omega is any algebraic section of the full commutative bundle, or just the first?
No, for the definition of the Hodge cycle and the Hodge locus, I will now use this subfield. But a priori, period is any differentiating any algebraic differential form over any cycle. For me, in this course, the period is just any differential form over any cycle. And a priori, it's a transcendental number.
But if it's a holomorphic form, does it have to be a holomorphic?
No, that's the point. That I will be back. They are actually much more than holomorphic forms. They are algebraic, given by algebraic expressions.
Then it has to be in F upper M of this bundle.
F upper
M.
But F upper M for me is.
Yeah, all right. So
you're this is just a special period for.
Yeah, you're assuming that.
This is.
Yeah, he's not assuming that you're dealing with the holomorphic top form.
Yeah, exactly. This is the point. The holomorphic top form, I don't need algebraic theorem homology. You don't care about Grothendieck theorem, that's okay. Because the holomorphic N form is already given by algebraic expression. But the point is that what I'm saying that there is a basis of this one given by algebraic. There is no global algebraic, the only global algebraic differential forms of the whole homology is just this one. But what I'm saying, there is a trick due to the Lean and Grothendieck that everything here you can express it by algebraic differential forms.
Oh, okay.
Maybe in this context, the way that you see this one is this one. You take this one in family and you make derivation of the differential form. Then you will not stay here, you will go forward. And this is a way to, one way to capture this algebraic theorem homology. It is not the way that I will put, actually this will appear, but one way to see this all other period is just making derivation, and there is the Picard-Fuchs equation.
Yeah, so there's the diagram method that Candelas introduced, which I've used recently, well, a long time ago, and again recently for number theory applications. But that's what you do. You end up getting access to the entire basis of algebraic differentials.
And when Chuck also said, in this physics mathematics literature, you don't need an algebraic theorem homology, which uses something called hypercohomology, because at the end, using this just top form, you manage to capture all the theorem homology. But in general, I will introduce this algebraic objects in the future lectures. Okay, so and as you see, I am really using this one because at the end I am claiming that these are holomorphics, and even if you take the other periods. And okay, so let's go. So maybe I make the definition of Hodge cycle. This is not the way that people write it, and that's why I have to. So let's say that's an even. So Hodge cycle, then it will be just. Maybe I just define in my special fiber, but then we can also define. Maybe something also I have to say. The homology with Z coefficient might have torsions in the whole course, except when it is mentioned, the homologies are up to the torsion. So just cutting out the torsions. The torsions have a different history. Anyway, so this is it's called a Hodge cycle. if the integration, so of, let me write it, m2 plus 1, h m theorem, x0 equals 0. Maybe I explain this one. So if you want to see this actually composition stuff, you have this middle one, and then you have this bigger middle one before the middle one. And this guy is exactly the one, say, before the middle one. Here, yeah. 2 plus 1. So this means that whatever differential form you have the, before the middle piece of the Hodge composition, all the integral must be 0. And if you already know the classical definition of Hodge cycle, this is the same. You just do the concurrent dual, and then you will land on the classical definition. But one idea of the mini course is that really it is still this old language of integral is useful, and actually the usefulness came back after many folks in physics, because okay, anyway. So since I have defined the Hodge cycle, then I have also defined the Hodge locus. So set theorem, it will be actually an analytic scheme, but let's first write as just as a set. Okay, what will be? So if you feel better, for example, if you take just the basis for this one, then that amount of integrals must be 0. And then let's introduce the Hodge locus. So I will take this family of cycles. So delta 0 will have monodromy, and then I will take its monodromy. So my notation of delta means the family itself. So delta then will be just the points in the usual topology, such that your delta 0, when you go to delta t, then it is still Hodge. So it will be then repeating the same thing here. Then it will be. Okay, let's start again. Okay. So this means, what this means? Okay, the delta t. This means that you have the family delta t, which is topological for any t, and that then you are interested just those t which delta t is still Hodge. And this is actually an analytic variety. So maybe let's see how this happens. For this one, let's say take omega 1, omega. Just take a basis of this piece of filtration. Omega, let's say h sections. Let's say actually there are algebraic sections of fm2 plus 1 hm. This guy, such that, okay, so when I'm talking about sections of this guy, it will be always in a Zariski neighborhood. This means that these are defined in a Zariski neighborhood of 0. Maybe to shorten my writing, I will write. And then such that at such that okay, that's what omega 1t, omega 2t, omega. So this is ht. So this omega just was family of differential form for the basis of this guy. after, let's say. Which, then I will not. Something that I will do, sometimes I will just write the filtration without which cohomologies, it is clear on the context. So that if you take a basis, okay, I will make a picture, then this width delta is just t in t0, such that omega 1 delta t omega h delta t equals to 0. So it is the zero set of, let's say, H holomorphic forms. And remember that all these guys are holomorphic forms, holomorphic functions from T0 to. So it is not at all algebraic, because something that during the course I will do it, for many interesting families, I will write the explicit expression of these holomorphic functions as power series. Of course, there are many examples, hypergeometric functions and so on, but something that I will need in the case of hypersurfaces, and it is kind of new, that it's possible to write down the Taylor series, give closed coefficients for the Taylor series of these guys. So by definition, it is an analytic variety, and actually I will consider it as not just as a set, but in some sense as a scheme. And why? So, and what the scheme structure comes from exactly the equation. I mean, these equations matters. The ideal generated by these holomorphic functions might not be reduced. It must be the worst, a very bad ideal. So at the end, the function space of my O by B delta is just this one, maybe, yeah? The ideal generated by these guys. So what is this? This is germs. Oh, sorry. This is T. Germs of holomorphic functions in a neighborhood in here, and this is a Noetherian ring, like, and at the end, if I start here by delta 0 Hodge cycle, then this will be a non-trivial ideal there. So, and as I said, this ideal is not necessarily reduced. Therefore, I will talk about the tangent space of this guy and so on, but the tangent space as a scheme and not as a variety, as a analytic variety. So this is the, let's say, this is the concept of Hodge locus, and something that during the course I will do it. And okay, this will include a lot of interesting objects, but something that I will redefine. I will a little bit generalize this one, in particular, to include something called this jump locus, which Chuck and Squatter, they have used it, to include this kind of interesting objects also. And but for the moment, this definition would be enough for me. Of course, for example, you can take more Hodge cycle and so on. But let's push forward with this one. Okay. Maybe, okay, that's it. The of Hodge. Okay, cycles or classes, but let's mix it. There is thresholds, so you find the class. So I will make a little bit different definition also. This will be useful later. There is this Hodge locus, and there is the locus of Hodge cycle. This is a little bit different, and let's see what is this one. So you have this family, And then what you do, so the point is that this usually this parameter space, you can artificially enlarge it without any reason. For example, one way to enlarge this parameter space is like this. You define T tilde total space. Oh, okay, so all these shifts are free. So there are vector bundles, and then you can associate the total bundles across the total space. So maybe the vector bundle. So now I know from the language of free shifts, I went to the bundles. M2 actually. Oh, okay, yeah. H and there are. So what and you have, you have this T, and what is the T tilde? It is just over each point you have let's say you substitute this the whole this F M and you see that this is the one after the piece of iteration that I give it is H M there are this is just M F M T that's half of that. Oh, okay, yes, that's it. And then so the point here. And that then you can make this let's see, the direct product of this one over T tilde. So in any case, by this construction you go to basically this is the same family, but it has more structure. So the locus of Hodge cycles is just, let's say, Hodge locus in this bigger parameter space. This is just, of course, then you have the zero, then you have to take, there is will be zero here also. Maybe I explain this one. And what is this zero here? So you fix zero here is actually contains the point current dual of delta zero. So you make you take the Poincare dual, you go to the cohomology, and then you have to use the Lefschetz 1 term, and then you get some point here. So the delta zero at the end will give a point in this space, and then you will call it zero. But maybe we return back later. So the Hodge locus, this will be Hodge locus in theta. And there are many theorems. Usually, when you prove some theorem here, it is easier to just make a projection here. But if you prove some theorem here, not necessarily you have proved something here. And this is now I will take the main example of this phenomenon. Okay. And I am telling also this one because you see, I will tell that this T tilde is much more useful this space. And actually, I will introduce even a bigger space, and I will make kind of propaganda. This bigger space are even more useful than this T tilde. And there's this theory of holomorphic formulations, variational holomorphic formation with certain with Hodge loci will appear this way. But at least this T tilde is a kind of classical. So, okay, so maybe the first non-trivial theorem in this topic is to Cattani-Deligne-Kaplan, 1995.
So among every fiber of this total space of that bundle, the fiber of x tilde over t tilde is the same.
Yes, the same. Yeah, of course.
So this locus is just a I mean, is it just pull back the?
No, I'm going to make a picture. Okay, maybe I make a picture and then you will see what is the subtlety in this bigger space. So maybe let's write down. Let's see that this is the V delta of U. Okay.
Yeah.
So in this bigger space, the singularities of Hodge locus, it's a kind of resolution also. So this means that this V. So maybe I have the locus. Maybe I denote this one V with the same delta tilde. So this means that when you project the Hodge locus from upstairs to downstairs, there will be a lot of singularities produced. But of course, the B delta upstairs might be singular also, but it is at least less singular than downstairs.
Sorry. If 2 points in t tilde are mapped to the same point in T,
Okay.
do you,
Okay.
the organic space acts as the same space.
Okay. Maybe the explanation that I was saying, this was the global picture. Maybe I write the Cattani-Deligne-Kaplan and then I return back to the Noether-Lefschetz. Okay. So maybe first I write this one and then. The locus of Hodge cycles is an open subset. This is usual topology of an algebraic sub-variety of T. Maybe I will explain the picture.
By Euro's origin, kind of.
Yeah, usual analytic, we take that. Usual or analytic. And maybe let's say equivalently, B delta tilde is the zero set of regular. So now this regular, the framework of algebraic geometry, just let's say quotients of polynomials if you embed your T somewhere. Regular functions in T as an algebraic variety. And maybe I said corollary. Maybe I write the same statement here. Maybe I put also this picture here. So the point is that this picture actually it is the global picture after the. So the Hodge locus a priori is maybe it can be just this one, okay, and locally a priori there might be no difference between the both Hodge locus and the locus of Hodge cycles. But when you consider the global Hodge locus coming from this theorem, then two branches, let's say two branches of the global Hodge locus upstairs might go 2 points. Two different points might go to the same point if you consider the local this global object. This let's say this algebraic variety. And maybe I have to write this one also. There is a okay, maybe there is an algebraic. That maybe that's a T, tilde, algebraic variety. Okay, V. Maybe I write the same things about V for T. There is an algebraic variety V such that 0, we get is unreducible So maybe let me explain once again the picture. So the basic idea is that these local analytic things are parts of algebraic objects. Just but downstairs, this global algebraic object might be irreducible, but when you look locally around the point 0, it might be just an irreducible component. But globally it is irreducible, but locally in the analytic topology it's just irreducible component. But upstairs it doesn't happen. So this guy is really open set. So if you make a neighborhood of this one and intersect with the global algebraic object, it's just you will get this yellow one. But here, local Hodge locus, you just see this one. But
yeah, so you're saying it's not necessarily smooth up above,
yeah,
but it has this good property.
yeah.
What? I get the picture, but I'm still confused why the picture looks like that. I mean, if the picture looks like that, then...
Maybe this one happens at the kind of monodromy. As you know, the monodromy,
but
if you take the Hodge cycle, you are making the monodromy along this one and return back, you get new Hodge cycle.
It's probably by something the definition. So it seems that from the definition, if two points lie on the same point over T,
Yeah.
then the fibers, the fiber
This
of
means that you have two
x
Hodge
T are the same. You have the same x sub T.
Yeah, you have the same x of t, you have the same fiber of the
And you're
relation,
looking at
but
the
you have
same-
2 points, and these 2 points are 2 Hodge cycles.
You're looking at the same delta? No. Also the same.
No.
Okay.
So the point that in this one, the delta of this one is different.
So what is the delta? So you said T tilde is defined to be the locus of Hodge cycles is defined to be the Hodge locus in T tilde.
Yeah.
So in that Hodge locus, you need to have some delta in your definition, right? So
Yeah, exactly.
What is that?
What is the delta?
Yeah, what is that?
You just take, let's say, here or either here or here. You just take the delta of this one and you take the monodromy of this one along this one. Since this is Hodge locus, its monodromy still is a Hodge cycle. And when you return back here, you still have Hodge cycle. But of course, it might be different from the original one. That's why you might get these two different branch separated from each other.
So it's different delta.
Yeah,
At
different.
one nodal point, you have two different deltas.
Yeah, exactly. So this. Okay. Anyway, then as I said.
So, Hossein, I think it's just a notational confusion, right? Because it is a different delta, but the notation writes down a single delta.
Yeah. Okay. So let me say. So this bigger one, I will call it V tilt. That's a bigger. So look at the open subset of an algebraic V tilt. So the local object is called, I call it, this local thing is called V delta tilt, and the same way this V delta, but the global object is let's call it just a V.
And there you go.
You have chosen a delta on X, and in order to define the Hodge locus in T tilde, you need a delta in X
Yeah.
tilde.
What is the delta?
What is that?
You take the Poincare dual. You take the Poincare dual of delta 0, you will get the point 0, and the fiber is the same. So the delta upstairs is the same as the previous delta. So at the end of the xt over here and the over here is the same. But maybe let's me another. So maybe we can also tell in this way. Upstairs, the point itself contains the data of delta, but downstairs we choose also delta.
But delta has to be Z coefficients.
Yeah, but as I said, we go when it is a Hodge cycle, when you do form per dual, and you go to the algebraic theorem homology, then you will land on exactly point here.
That delta you're using on x tilde doesn't have to be z.
X tilde.
That x you're using on x delta, x tilde doesn't have to be in the z quotient homology.
No, it is this. I mean, the fibers they do not change. I mean, they are just as I said. If you maybe I make another picture here.
Yeah, I mean, he said it, but he didn't write it. But when he was defining a Hodge cycle, he should have blurred it to be a rational cycle. So, anyway.
I think
So maybe 0 here,
right.
and then let's make this picture here. So let's take this and here, and here I had to add this delta 0. So how I go upstairs? So at the end over here, let's say that it doesn't matter what is this one. For this one and this one, the x is the same. x0 is the same. Okay. So, but what is this 0? You take this you were in a HM, you go to the cohomology, and then this induce, I just an element in HM theorem F2. So first you have to, actually this is a translation of the Hodge cycle from here to the classical one. And this means that element here, this means that it gives a point. So this point will be corresponding to this one. And so, but at the end, the delta is the same. Delta 0 for both this point and point is the same. Okay?
Yeah.
And okay, maybe since we started late. Okay, that's it.
Can you say again this corollary?
So the corollary is.
Where is there tilde or where is there not?
So this means that at the end, I prove the algebraicity here. The same algebraicity here is true, but I have to be careful that my Hodge locus is not some open set. It's an irreducible component of the local branch of the algebraic variable. That's why the statement becomes a little bit different. Here it becomes really an open set, but here it's just irreducible component of the local branch. Okay, so that's it. Maybe okay, something that I have to tell. Well, this is a consequence of the Hodge conjecture. But since really in this course we will not deal with the Hodge conjecture, but maybe I write another consequences of the Hodge conjecture, which is completely open. And at the end, this has to do with this algebraic object. If is defined over, let's say, K field, a subfield. For example, family of hypersurfaces is defined over Q, rational numbers. Then all of them, V field, are defined over K.
Which conjecture is more open? D1 and hypothesis.
Huh?
I'm curious, which conjecture is more open? D1 and hypothesis also?
No, all of them. I think the hypersurface is. I think this is as difficult as the Hodge conjecture itself, but it must be easier because you don't construct algebraic cycle. But this one is also might be difficult, but maybe it's a little bit easier because at least the difficulty of the Hodge conjecture is because of we don't know any way to construct algebraic cycles, and this doesn't involve any construction of an algebraic cycle at least. But anyway, the proof of Cattani-Deligne-Kaplan is purely transcendental, and at the end you don't see why this kind of phenomena must happen.
But are you saying this is implied by the Hodge conjecture?
Yeah, this is also implied. Hey. By some Hilbert scheme argument, you can prove also this one, but the proof is purely transcendental based on SL2 orbit theorem, Schmidt's independent orbit theorem, and so on. So you don't see why this happens. Let's say implies. Okay, maybe for example all these maybe we can return back to this a bit more detailed. Okay, maybe. Okay. Okay. Well, I will put. As I said, one of the main aim of the mini course also to introduce this bigger modular space, not this one, but even bigger than this one, which has been useful in physics and mirror symmetry stuff. But we will return back this one. But let me at least put a theorem. Let's. Okay, even that I have not defined the notion of global Hodge locus. Maybe let's make a definition. In both cases, we give or call the, let's say. It is just definition for not couplable locus. So at the end, what this means is that when I'm saying that some algebraic variety of T is a component, what it means. This means that there is I have a local analytic variety on that guy with the property that I mentioned. So. Well, of course, you can define a global Hodge locus and so make this definition, but for now, it just means there is open set, small open set here, either here or here, such that this phenomena happens. Okay, so maybe at least I put one theorem. And as I said before, we will back a lot of examples. Even so, I started with the general definition. Maybe I put one example. Let's return back to the case of hypersurfaces. And so the full parameters of hypersurfaces. So let's consider, let's say n, the dimension even. And then let's consider two projective, linear projective space of inside n plus 1. These are linear, given by linear equations. And let's consider x. Let's say in this way. I will define Tm. What is Tm? The locus of hypersurfaces in T in Pn plus 1 containing, let's say, containing two two linear cycles, Pn plus 1, such that Pn2 intersected Pn2 is Pn. So maybe I take a picture, so I'm considering what? So this is my bigger space, and then I'm considering a loci called Tn. So what is this? So the T this loci correspond to xt, and inside xt I have Pn2 check, and they intersect each other Pn. So in some sense, if I make the picture of xt, it is just 2. And at this point, it's just projected space P. And
So
I want to
this,
just
this generalizes characterization of surfaces in P3 containing a pair of skew
Yeah.
lines.
this is the most, let's say, in the future I will do also more combinations of PMs, but the classical, for example, two lines intersecting each other, all these things are classical. Classical
Skew lines where it's skew.
Are you fixing the linear spaces, or are you saying Tn is the locus of hyperplanes where there exist two linear spaces? Or are these fixed?
These are linear space subspaces. Hypersurface which contains, for example, case of unequal surfaces. Surfaces containing two lines.
But I'm saying, are you fixing the two lines, or are you
No,
saying
no, it's
surface
not
limit?
fixed. It's
You're
not
not
fixed. It's
that
not fixed. So,
You're fixing M.
no, exactly. N and M are fixed. That's why I put here N. So, in the case of surfaces, there are two loci. Or intersect each other, or in one point, or they do not intersect. And M equal to -1, so the one notation P -1 is just the implicit. This is the first time I was wondering that P -1 is also useful notation. I never thought that P -1 I could use a P -1 article, but I've never seen it somebody somebody using P -1. Okay, anyway, so maybe let's say, okay, there will be a lot of theorem partially proved by computer. Maybe I did just a sample theorem, and then let's say maybe I write the case of Calabiot NT4. So dimension 4 and degree 6, and then let's say I put m equal to -1 and 0. So I'm considering sextic fourfolds containing two P2. One of them, the two P2 do not intersect each other, and the other case, two P2 intersect in a point. I'm not considering two P2 intersecting in a P1. This will have another story. So for example, in this case, Tm is a component. Maybe I have to say that this is me and my students. And this, so I said the sample example, this is a component of Hodge locus. So maybe I explain that this is some non-trivial statement. So what is the content of this this theorem? As I said, let's say, just take a generic xt. As I said, I have just pointed to some region of the which okay, that's it. Just take two P2. Maybe I take this x0 will be generic. The P2. Maybe I take the case n equal to 0. So this is just a point. P0. Okay. Then I perturb it a little bit. I go to xt. Topological cycle you can produce. So then this, for example, if you take delta, the homology class of this P2 plus P2 check. And actually you can put any coefficients, doesn't matter, R check, R I'll check Z. And I will put, let's say, not 0. Both of them not 0. For example, some of them. Topologically, you can transport them to some cycle delta t. And then you may ask, okay, is this Hodge cycle or not? And the affirmation is that this is the Hodge cycle if and only if you have deformed, if this is 0, you have deformed just in this TM loci. So if you go outside of TM loci, it's no more Hodge cycle. So for example, if you put, let's say, T here outside of Tm, then it will be no more Hodge cycle. And the only way that you can keep this guy Hodge cycle is just living in Tm. And of course, when you live in Tm, always there are two P2 intersecting P0, and then your Hodge cycle present. And these statements are non-trivial, and it's a part of, let's say, a conjecture originally called by Grothendieck variational Hodge conjecture, but these are a kind of stronger version of variational Hodge conjecture. I started to call it alternative Hodge conjecture because it's a kind of trying to verify the Hodge conjecture by just a small perturbation. And yeah, I think I will stop here. So, as I said today, I made let's say just a definition, trying at least to put a theorem. And there will be, I will introduce to introduce a lot of computation with the case of hypersurfaces. In particular, I will try to concentrate on the concept of Hodge locus near the Fermat variety. And I have to a little bit analyze all these Hodge cycles of the Fermat variety and so on. And if some pieces of the talk were ambiguous for you, I think during the course it will get better and better by explicit examples. Because I start all these things by explicit examples. When the explicit examples are clear, then you can trust the general notation and do. Okay, then next week. Thank you.